Okay, we're going to go ahead and today start solving trig equations. Now, for all of the values that we're going to do with these are always going to be for exact solutions. So let's go ahead and just dive right in and talk about what we're doing. We're going to refer back to the unit circle, which is why it's back over here in the right-hand side. So if we start with the equation, 2 times the sine of x minus 1 is equal to 0. We're going to solve these equations exactly the same way we would if all of this that I have here in this pink box is u. We want to get this entire argument all by itself. So the first thing I'm going to go ahead and do is add 1, then divide by 2. When I do that, what I go ahead and have is adding 1 will give me 2 sine of x is equal to 1. Divide both sides by 2. Gives me, where is the sine of x is equal to 1/2? Well, if I come over here and look at the unit circle, that happens 2 different places. And that's what you have to be really careful about if you're solving this in your calculator, because if you do that, you'll only get one of the solutions, which means you would only go ahead and get half credit. So if I'm going ahead and looking at this, where does that happen? Well, sine is our y value. It is equal to 1/2 at pi over 6. And it's also equal to 1/2 in the trig world. All students take cash, so that is also positive in the second quadrant, so it's also positive here when the y value is equal to 1/2. So what I do know is, where does this happen? This happens when x is equal to pi over 6. It also happens when it is equal to 5 pi over 6. But it doesn't just stop there. Every time I go through a revolution around the unit circle, what ends up happening is I get all of those other additional angles. So the question is, how do you go ahead and write your answer if there's an infinite number of solutions? So what you have to do here is go ahead and think about this. Let's take our first solution of pi over 6. At pi over 6, I'm going to come round, and that second solution is pi over 6 plus 2 pi for one revolution. Then I'm coming it around again, and I'm going to another revolution, and that would be at 4 pi. So the way you write this final answer would be 6 pi plus that 2 pi n. N stands for the number of revolutions. That would be for that first answer. Then I also have my other piece where sine is equal to 1/2, and that's 5 pi over 6. That also has to be written with that plus 2 pi n. And this would be for the entire set of solutions over all values of theta. There will be some times where the value will be defined only between 0 and 2 pi, and if that's the case, then the only answers you would need would be this first box. All right, let's go ahead and try another one. All right, so the next one we're going to look at is tangent squared of x minus 3. So again, the first idea is think about what you're solving for. We want to get this tangent squared of x all by itself. So when I go through and do that, I just go ahead and add 3 to both sides. And then you get the tangent squared of x is equal to 3, solving for this. Now, it's really important to remember that this is the same thing whenever you see trig functions written this way. This means the tangent of x squared is equal to 3, and that is what allows me to take the square root of both sides. And then I can go ahead and say that the tangent of x is equal to the square root of 3. Now, where does that happen? Remember, the tangent is equal to, of any angle, is equal to y over x. So I'm looking for the values where the sine is equal to the square root of 3 over 2, and it's positive. All right, so that happens here. And because the tangent has a period of pi, which is different, because by the time I go ahead and do half of revolution, so I come down here for my next value, which will go ahead and be at 4 pi over 3. But if I'm looking at what's going on with the tangent, I know that my first value was up here, where my tangent is equal to pi over 3. And just add that n pi, and I can do that because the tangent has a period of pi. So what I mean is that if I do pi over 3 plus when n is equal to 1 of just pi, I'll make that 3 over 3, and that gives me my second solution of 4 pi over 3. And as that tangent keeps revolving around, it will give me all of those values. When we're doing this, n is always understood and stated to be any integer. Let's go ahead and look at a few more of these. So what I have for the next one is where we have 2 times the cosine of x plus the square root of 3 is equal to 0. Again, we're getting this argument all by itself. So I'm subtracting the square root of 3 and then dividing by 2. When I go through and do that, I'm going to go ahead and get the cosine of x is equal to minus the square root of 3. Divide everything through by 2. So where are the values of the cosine of x? Where does that equal negative square root of 3 over 2? Now, for those of you that say, well, I can just go ahead and plug that into my calculator and get that answer, you're absolutely right. If you go ahead and do that, you will go ahead and find that is equal to 5 pi over 6. But the problem with this is it's not going to give you that second value. So we know cosine is negative in the second and third quadrant. So the other value where my cosine is equal to negative square root of 3 over 2 is at 7 pi over 6. So we have those two solutions for this piece, but we also have to remember that if we are talking about over the entire interval, it's plus 2 pi n for both of those given solutions. All right, so there is one more I want to go ahead and look at before I look at and talk about something that's a special case here. So if I have 3 times the sine of theta plus 5 is equal to negative 2 times my sine of theta. What I have to do with this first is I actually have to collect the like terms, because I need to get the sine all by itself on one side of the equation. So the way I'm going to go ahead and do this is I'm just going to go ahead and, let's go ahead and just subtract 3 times the sine of theta from both sides. It does help to think about this equation as the same thing as saying 3x plus 5 is equal to negative 2. When I do that, I'll go ahead and have 5 is equal to minus 5 times the sine of theta. So after you go through and divide both sides of this equation through by negative 5, what you're going to end up with there is that negative 1 is equal to the sine of theta. Well, that only happens in one place, where is the y value equal to negative 1, and that's down here at 3 pi over 2. So this theta only has one answer, that 3 pi over 2, but you still do need to add that revolution going all the way around the unit circle. All right, for this, I want to talk about something that happens that's really important that we realize when we're talking about these equations. If I have the sine of theta is equal to -5, there's no solution with this. And this is really important. If we go back to the graph of our sine, what happens with the graph of our sine? Our normal sine curve comes around like this. And we know that maximum and the minimum portion of the sine is +1 to -1. That's the entire range of the sine, correct? So the whole range of the sine only goes from 1 to -1. Both of those pieces are included. So what this means is this idea that the sine of theta is equal to -5, it's not possible. It's outside of possible solutions for the sine, so there's no solution for this. Another one like this that has no solution would be if I have 2 times the secant of theta is equal to 1. What happens here? Here I have the secant of theta is equal to 1/2. Now, this is the reciprocal function of the cosine. Cosine has the same type of graph, but with the cosine, just starts and ends in different places. So the cosine is going to be like this, right? Up to here. So what happens with the secant? Your secant function starts here and then goes up. Is what we are looking for that. But again, the cosine goes from 1 to -1. So there's nowhere inside this where the secant of theta is going to equal 1/2. So this is another example where theta does not exist. In theta, there is no solution. Watch out for these. Always pay attention to what the domain and range are when you're talking about the trig functions.